job, Benjamin. You passed your first test of the presentation. Let's hear about launch vehicles in Julia.
All right, thank you very much. Sorry for the technical delay. I'll be talking about ignition point reachability for aerodynamically controlled reusable launch vehicles. The basic problem is something that most of you have probably seen before from SpaceX et al. We have a reusable launch vehicle that has an aerodynamic phase, is descending towards a launch pad, then the engine reignites, and then it actually lands on the launch pad, sort of touching down softly. In this talk, I'll be talking about the phase of flight between supersonic retropropulsion, so when that cuts off to when the vehicle actually touches down. The interesting problem that we're investigating here is what happens if the engine doesn't turn back on again. And we actually saw this quite recently with the first flight of New Glenn, wherein the proximal failure of that vehicle was that the engine failed to relight, and then the vehicle went aeroballistic and hit the water. Especially if we're landing on land, we would really like this to not happen into something expensive or important or full of people. So the problem that I'm going to be talking about in this presentation is where can we put that ignition point? Where can the rocket decide to relight so that it can still land at the end? And then once we have this volume for a given initial condition, we can go, oh, this part of it doesn't make sense because it flies into something expensive. Or this part of it is safer, type of thing. And still guarantee dynamic feasibility all through for any ignition point that's selected in that volume. There's three aspects to this problem that I'll be talking about. There's the underlying dynamics of the vehicle, there's the trajectory optimization that identifies feasible trajectories from the initial condition to the landing site, and then there's the reachability analysis problem that allows us to identify that intermediate position where we relight the rocket engine. So looking at the dynamics of the vehicle first, the vehicle is an axisymmetric reusable launch vehicle modeled in 5 degrees of freedom. We have translation, pitch, and yaw with an artificial damping term to slow down the pitch dynamics. We have mass and moment of inertia dynamics, so the vehicle's moment of inertia changes as you deplete the fuel. It's linear in mass. And then we assume a constant center of mass as the fuel has been mostly depleted, so it doesn't change too much. Because it was easy and not ITAR controlled, all of the aerodynamic coefficients and aerodynamic data came from Kerbal Space Program. For the aerodynamic modeling, what we do is we look at it as a combination of fin and body contributions. Both of them are modeled using lookup tables. The body is very straightforward. The fins are a bit more of an adventure. The way that we deal with the fins is that the fin forces are actually calculated in the wind frame rather than the body frame, with the rotation fixed by our 5 degree of freedom formulation. Since what we do is we fix the rotation of the vehicle around its axis in the inertial frame, and then this forces the orientation of the fins to be one specific configuration. The interesting problem here is how do we command the lift force? The traditional way to do this is to say the angle that the fins are deflected to, because that has very direct meaning to the physical plant. But the problem is that you run into a lot of unpleasantness. So stall nonlinearities, they're going way up. This is strongly coupled to the angle that the body is at relative to the wind. It just becomes very unpleasant. So you end up with this highly nonlinear mapped lift force. The solution that we have is that our control variable is actually lift force directly. What we do is we non-dimensionalize the lift force based on a lookup table as a function of the Mach number, and then multiply our control variable by that. We then apply a box constraint on the allowable non-dimensionalized force to enforce what is dynamically achievable by the fins to create a nice convex volume within which the fin actuation is feasible. We then calculate the induced drag coming off of the fins producing this using a lookup table drag polar. So that's the overall model. So I'll now talk a little bit about how we then do trajectory optimization over that model. What we do is we enforce initial and final state constraints that define the start and end of the trajectory. We apply a force limit so that the vehicle is never subjected to excessive aerodynamic forces, as well as min-max gimbal constraints on both the engine once it relights, as well as the controls. We have aerodynamic and state constraints consisting of a maximum dynamic pressure, a maximum productive dynamic pressure angle of attack, which essentially defines a maximum allowable normal force of the vehicle that could rip it apart, and maximum angular rate so it can't pitch over too fast, and a minimum field constraint. Constraints in green, which are functions of particularly fast aspects of the dynamics, are enforced in continuous time. The constraints that are in black are enforced in the discretized version of the problem. The way that we do continuous time is constraint satisfaction that we enforce this is by using the underlying diffie-q solver and adding an additional state to it. What we do is we detect the zero is we introduce a nonlinear function of the constraint that adds up the penalty, and then introduce a callback that then detects the nonlinear transition to ensure that the solver captures this well. We then require that this additional state is 0 as part of our ultimate underlying boundary value problem solve. Then we do time dilation to get from a fixed final time problem to a two-part free final time problem, so the two independent parts of the trajectory can have different times. And then we do an overall non-dimensionalization of the problem by a scaling factor. We solve this optimal control problem through a very standard successive convex programming approach over a multiple shooting transcription. I won't go into the details too much about how this works. But I will talk a bit more about how we did the implementation. So what we do is we break our overall trajectory problem down into 41 nodes with 42 individual shooting segments. And with the fully transcribed problem and the fully augmented problem, we end up having 19 states at each of those segments. So we end up with 13,000 non-zeros in our transition Jacobian. We then compute all of these in parallel using SciML sensitivity with automatic sparsity detection, automatic sparse forward sensitivity analysis. This is much the same mechanisms that Chris was talking about in his talk earlier today. This, on my laptop, would take about 30 milliseconds to solve. We then give this problem to a subproblem solver, which then solves the linearized version of the dynamics and ensures feasibility of the intermediate solution, which then normally takes about 15 milliseconds using JuMP or Clarabel. As an example of a trajectory that's produced here, this is targeting a minimum field objective. So you can see here that along this trajectory we're satisfying all of the state and dynamics constraints. In particular, something that I'm very happy with is how we just barely kiss the dynamic pressure maximum limit in the center in the left, the middle center left one. Okay, so then the last part of this is reachability analysis. So if we have some reference trajectory where the rocket was able to relight and it was able to land at the end of it, essentially the reachability analysis problem ends up asking how far can we move this point around and have it still be able to satisfy all of our constraints. The way that we do this is by taking a reference trajectory and then perturbing it. What we do is we randomly pick a direction of perturbation for the ignition point and then push it along it. And then we just do this repeatedly, building out a convex polytope of points that we've discovered that are sort of extremal. I will skip over the details of how we actually transcribe this into the trajectory optimization problem, so that I can show you an example of a polytope. So here we have the 3D version of all of the trajectories and the extremal polytopes. And on the left here, these are sort of the reachability trajectories, so the extremal points that we've discovered on the surface of the polytope as they worked their way out to it. In terms of running time, each one of our trajectory optimization problems takes about 1 to 2 seconds, with outliers that weren't screwed over by the operating system of taking about 4 seconds. It took between about 15 and 30 successive convex programming iterations to converge. And those reachability results were developed out of 10,000 trajectories, which took about 4 hours. Okay, so in conclusion, I talked about the 5-degree of freedom reusable launch vehicle model with body and fin lift and drag. I described an approach to doing non-convex approximate reachability analysis where we're extremizing only a small portion of the state, thereby avoiding the curse of dimensionality. And some future directions that we're interested in are moving to a more realistic attitude control model where we actually have a nonlinear attitude controller. We're investigating an NDI approach to slow down the attitude dynamics in a physically realizable way, using some of the new boundary value problem infrastructure in ordinary, or not diffie-q, it's just diffie-q, as well as doing higher level sampling direction selection. Okay, thank you very much. Any questions?
Yeah, thank you, Benjamin. Unfortunately, we don't have time for questions, so but you can catch him, I'm sure, right? He's around. And let's move on.
Hopefully this works for you. Let's see. Yeah. Okay, good.
Seems to be working.
Looks like it's settled down.